In this video, we're going to learn how to sketch the graph of a piecewise defined function. Now, if you remember back to graphing linear functions, we could choose any x value that we wanted to, solve for a corresponding y value, and then use those points to graph the line. However, when we're working with a piecewise defined function, we have to be a little bit more strategic about the choices that we make for x in order to make sure that we find key characteristics of the graph. So the first thing that we want to do when we're trying to sketch the graph of a piecewise function is we want to find the domain of the function. Now remember, the domain tells us where the function is defined and thus where the graph is going to exist on the rectangular coordinate system. So in this example, we see that we have two pieces of definition, and that for the top piece, it is defined for x such that x is less than 1, and then the bottom piece is defined for all x such that x is greater than or equal to 1. So if we think about both of these combined and we look at them on a number line, so if you're a visual person, then a number line may help you. So the top piece of definition tells us that we're including everything that's smaller than 1, so all of this stuff. And the bottom piece of definition tells us that we're including 1 and then everything greater than 1. So between the two different definitions and two different pieces of domain, what we have is all real numbers covered. So the domain for the entire function is going to be all real numbers, or negative infinity to positive infinity. So what that essentially tells me is that my graph is going to exist on the entire x-axis. So when I go to graph, I need to make sure that my graph covers all values of x. So now we're ready to actually sketch the graph, and in order to sketch the graph, we want to first determine how many different pieces of graph we're going to have, and that's going to be based on the different pieces of definition. So you'll notice that in this particular function, we have two pieces of definition. We have the negative 2x plus 3. We also have the 3x minus 2. So that tells me I'm going to have two different pieces of graph. And then I also want to figure out what's the basic shape of each of those pieces. And the shape of the graph is going to be dependent upon the type of function that's represented. So negative 2x plus 3 is a linear function because x is raised to the power of 1 and nothing higher. So that tells me that the shape of the graph is going to be a line. On bottom, I have 3x minus 2, which is also a linear function. So that tells me that this piece of the graph is also going to be a line. And that helps me out a couple different ways. First of all, it tells me that I only need 2 points to be able to graph these two pieces, because we can graph a line with only 2 points. It also is going to tell me what kind of shape I'm looking for when I go to graph. So now that we know we have two different lines that we're working with, we know that we need 2 points to graph the top piece of definition, but we have to be strategic, because remember that we don't just need any 2 points on the line. We need to know exactly where does the graph start and stop. Well, because it is defined for x less than 1, it's going to start at negative infinity. So we're not going to be able to find that exact point where it starts, but we will be able to find the exact point where it stops or terminates, because I know that it's going to stop at an x value of 1. So if I plug in an x value of 1 to the top definition, then that's going to tell me the point where that piece of the graph is going to terminate or end. So I have negative 2 times 1 plus 3 is equal to a negative 2 plus 3, or 1. So when I plug 1 in, I get 1 out. So the ending point for this piece of graph is going to be the point 1, 1. However, notice that x can't actually be equal to 1 for this piece of the definition. So what that means is this is still going to be the point where our graph is going to end, but because x cannot be equal to 1, we're actually going to have to plot it as an open point and not a closed point. And that's going to tell us that the x value isn't actually equal to 1, it's just running right up to that point. So let's go to our graph, let's find 1, 1, and let's plot an open point. All right, so now we said we needed 2 different points to be able to sketch the graph. So we need to pick one other value of x. And because it doesn't tell me what the lowest point is, I can choose any value I want to as long as it is less than 1. Because any x value less than 1 is in the domain of this particular piece of the graph. So I'm going to choose f of 0. Just because I like to keep things as simple as possible, and keeping the point close will make it as simple as possible. So I end up with 0 plus 3 is equal to 3. So I have the point 0, comma 3. Because we plugged 0 in for x, we got 3 out for y. And because this is a point that is included in the domain, because 0 is less than 1, it's actually going to be a closed point. So we have an open point at 1, 1, we have a closed point at 0, 3, and we know that they're going to be connected with a line. We also know that x can be anything as long as it's less than 1, so our line can go on forever in this direction. However, it can't go past our open circle to the right, because then x would be greater than 1, and this piece of the graph is not defined for x greater than 1. Now we're going to do the exact same thing, but we're going to do it for the other piece of the graph. So we're going to look at the 3x minus 2. And again, the starting point, well, this graph starts to be defined at x is equal to 1. So we're going to start by plugging 1 into the bottom piece of the definition. So 3 times 1 minus 2 is equal to 3 minus 2, or 1. So we have the point 1, 1. And since x is equal to 1 for this piece of definition, this is going to be a closed point. We don't need to worry about leaving it open. So now, it was already open for the pink piece of graph, but since it's closed here, we're just going to go ahead and mark it as closed. It can't be both open and closed. So since it exists for this piece of the graph, it's going to be a closed point. Now, we need one other point to be able to sketch this graph. We can choose anything as long as x is greater than 1. So I'm going to choose 2. So 3 times 2 minus 2 equals 6 minus 2, or 4. So we have the point 2, comma 4. And again, it's a closed point because 2 is greater than 1, so it's in the domain. So we go to 2, 4, put our point. And again, we know that this basic shape is going to be a line, so we're going to connect these 2 points with a line. And because this piece of the definition is only defined for x greater than 1, our line can only go in the positive direction. Now, think about it in terms of x. Even though this is more positive for y, it's going up quicker, it's still going to the right, and that's the reason it's still considered positive on x. So the graph for this particular piecewise defined function would be 2 lines that kind of look like they form a V. Now, you'll notice that in this case, the 2 lines connected at a point, and that's okay, but that won't always be the case. Sometimes the lines will be completely discontinuous, and that's okay as well. And then our last step here is to find the range based on the graph. So remember that the range is made up of all of the y values. So if we look at our graph, our absolute lowest y value for either piece of graph is this point right here, which is 1. And then we have arrows that go up forever, so our highest y value would be infinity. Because there's a closed point at 1, we're going to include that by using a bracket. And then, of course, we never include infinity. We always use a parenthesis around that. If the pink piece of graph had remained without the purple piece, then we would not have included the 1 because there would have been an open point there and the 1 would not have been included in the range. But since the purple piece of graph did in fact close that point, we are going to include it in our range.